Kevin Bittenbender, company steward with Benson Wood. Passionate about working efficiently, Kevin has actively and successfully incorporated lean principles and practices into Benson Wood's operation. He has served as a team leader for the woodworking department and now oversees the design development, engineering, and virtual fabrication teams. As an innovator in a rapidly developing sector, we are thrilled that Kevin has joined us today to share his experience. Kevin?
Hello, everyone. Glad to be here, and I'll be talking a bit about the front-end process on mass timber jobs. What I referenced might not always be about mass timber, but a lot will be about panelized process, panelized products, offsite construction, parallel processing. But the front-end process is the same for these types of products as it is with mass timber. So the examples will definitely relate. There's kind of an early team engagement, which is critical for successful completion of these types of jobs. And additionally, this early work will reduce risk, as Chris was just talking about previously. I also heard Chris mention quite a few times about being proactive, engaging the team early in the process. And those will be some of the underlying themes that I talk about as well. I try not to read from slides, but this one's worth it just for this quote from Thomas Friedman of big breakthroughs happen when what is suddenly possible meets what is desperately necessary. I'm sure that everyone here is interested in alternative strategies for building within our industry. It's why you're here, right? And stick building and the concrete steel construction process on site has been the status quo for far too long in this country. But with new technology and new materials, there's a new and better future for the building industry. I share this presentation with Brad Nile from Anderson Construction out on the West Coast. And though we're two totally separate companies, we have come to the same conclusion about the way to build. We've done some really similar work, as you see in these slides, using similar materials and similar processes. And in both companies, something we call build it meetings are used well in advance of final construction to ensure that all of the details come together when it's time to hit the site. A little bit of history here. Over the past 70 years, many other industries have been improving, as you can see in this chart showing productivity per employee. However, it's not really the case for the construction industry. But with conferences like this and developing new ways to build that we have kind of at our fingertips, we're trying to address this level or even downward trend. Conventional construction methods have led to this downward slope in that previous slide. And for many years, we've largely been site builders in this country. Site building, as you all know, has weather and sequential challenges. Also, our country really hasn't embraced and celebrated the trades as they have in other countries, which has led to this decline in the skill set of the average person in the construction field. And unfortunately, this has happened for so long that the poor quality results have kind of become accepted rather than being the exception. So what can we do to change this trend? Again, that's why we're here. And many of us are making strides in many areas, but the improvements aren't really industry-wide yet. Building has challenges on several fronts, but we have new tools that can change this playing field. Better technology and new team formats and different materials, we can really find some good solutions. There are some common themes that evolve when considering these new building tools. Offsite construction brings us to a place where we can reach similar productivity benefits, more like manufacturing has seen in the past 50 years. Different new materials, mass timber being an obvious one, offer some real big advantages. And the underlying theme here is the different construction team, where we have all the players involved early on during the virtual construction process. By creating this virtual building team, we can benefit from parallel processing and well thought out designs that don't lead to rework in the field, like Chris brought up in some of his earlier slides as well. So again, some of the challenges listed on this slide. and to have some solutions to make this virtual building team possible. Before anything happens on site, we need to get good information from the site. Here's an example of 4 GPS monitors set up on a site to collect good information. And another picture here showing the process of digitizing data to drive construction in new ways, kind of connecting the real world to the digital world. This is definitely needed before virtual construction to document existing conditions and allow the electronic construction process to be accurate. And again, as I've been talking about, here are some of the solutions, focusing on fully digitized models built virtually in a very collaborative process with all of the team players engaged really early on. Other industries get this process, and once you build something electronically, you can take advantage of parallel processing by constructing components that come together in a final assembly process rather than all fabrication taking place on site sequentially. Here we see 2 examples of parallel processing with fully finished bathrooms being installed in a cruise ship, kind of in a pod style, and also with sub-assemblies being installed in the foreground of this picture, and then the final assembly taking place in the airplane behind. These are valid strategies for construction as well, as we've seen them work in other industries. So we have lots that we can learn from different people in many different countries or regions, and Germany and Sweden in particular are a bit in front of the US when it comes to CNC and offsite construction and mass timber construction as well. So we have lots that we can simply learn from how they've been building in the past 20 years rather than us needing to develop it all. Mass timber encourages and actually pretty much requires this different approach to building. With crane installation, CNC production of all pieces really requires the early engagement of design, mechanical, and construction teams too, to work out all of the detailing prior to assembly on site. In the left side, you see many beams visually on the screen, and then beams in the shop on the right side, more beams in the shop here, and the complexity of a project like this is only possible through digital fabrication. On this particular job, the Swatch building in Switzerland, to give some perspective, there were 14 modelers on this job, only 5 carpenters in the shop, and then 8 people assembling on site. So that kind of gives an idea about the balance of where the heavy lifting is on jobs like this. The question, does it have to be in the model, is often asked, and the answer is almost always yes. You'll hear me say that quite a few times in the next 15 to 20 minutes. And in addition to machine code that allows for CNC fabrication, you gain access to all kinds of other information once you have everything in the model. Things like cost estimating, energy analysis, ordering, shipping, planning. All of this can be extracted from the model itself if it's actually in the model. And with information in the model, we're fit for automation and ready to output to CNC machinery. CNC machinery is well suited to high repetition, as you see with the cheese boards on the left, dealing with large sizes as well, as you see in the middle example with a big shear wall being machined on a Hundiger PVA machine, and integration with the overall building too. On the right, you see some facade panels that will be installed on a building after the structure is up. And we're confident that it will all fit on site because the prefabricated structural panels and facade panels and any other elements all reference the same model. Different locations also don't matter when you reference the model instead of needing to reference the product on a job site. Everything still does have to come together on the job site, but there are some big advantages with being able to parallel process at different locations. Here you see a timber cutting CNC machine on the left at our facility in Walpole, and then a wall panel fabrication that is at a different location about 20 miles away. Both building materials for the same job, but at 2 totally different locations. Virtual building also offers a new level of complexity with precise milling ability translated directly from the model to the CNC. That way, decorative elements can be integrated into the building element as seen here in some of these pictures. In addition to decoration, precise location can play a role in efficiency as well. We have a mantra in our company of trying when we can to eliminate the use of a tape measure. So with information coming from the model and joinery incorporated, it can reduce all kinds of layout processes and have that be more automated with the parts that come right off the machine. Labeling is even possible on some machines to pass along assembly information from the model to facilitate final assembly on site. How you feed the actual material to CNC machines becomes part of this process as well. Using mass timber, we get into the realm where special material handling equipment is needed for longer lengths and larger sizes. You can picture these aren't parts that people just pick up and move around on a job site. And here's an example of a vacuum material handling robot used for feeding really long lengths of material to CNC machines. So now we'll dig into a few case studies here showing how the virtual building process leads to fabrication and finally assembly on site. This project celebrates integration of mass timber, steel, and concrete in a large shear wall at Oregon State University. All of the elements were shop installed, and site work was mainly assembly of these pre-built components. Here we see a snapshot from the model showing all of the elements built virtually and the real elements installed on site on the right. The shear wall in this project resists the wind load, and then boundary elements on the sides can dissipate energy in an earthquake. And the tension rods run all the way up to the third floor, making this kind of a flexible shear wall. The center rods can stretch enough to dissipate energy, and we actually have some sensors installed, you can see in the top right, that will detect stress in an event. And we're waiting for something to happen, but we'll see how it performs since we actually have some sensors that will record how it does perform. You can see here the digital twin of this particular project with the shear wall on the sides, huge glulam mullions, stair stringers having a moment connection at the landing, all built virtually and then shown assembled on the site on the right. Integration of mechanicals. Again, the question, do I have to model this? And the answer, of course, is yes. In order to model, you need to answer all kinds of questions. Unmodeled elements will almost always lead to issues. And these decisions and resolving these issues are much better addressed on the screen rather than on a step ladder on site. If it's in the building, it really needs to be in the model. And this is especially important for MEP considerations. The atrium on the left-hand side obviously doesn't want to be cluttered with all kinds of mechanicals. So it takes good planning to incorporate it all on one side of the building. Here you see the digital plan for what we were just looking at, built by the virtual team, obviously, well informed by mechanical trades. And here you see it in the real physical world as the plan is all coming into place. Having a good thought out plan really allows us to densify utilities and even sometimes incorporate them into visible locations in the structural elements. Here is the electronic space built by virtual fabrication team. And then here's the real space showing densified mechanicals on the right-hand side and integrated conduit and sprinklers into the structure on the left-hand side. And then a final picture showing what it looks like finished with the fully integrated mechanicals. So the complexity of the project and all that has to come together from various people creates this need for a large team that needs to come together really early in the project. For these projects we've been looking at, these bullet points are some of the considerations that need to be taken into account early in the building process. What the timber structure is like, code constraints, third-party certifications, All of this is critical to have engagement of the team as early as possible to have a critical, smooth final assembly on site. Here are some more examples of planned space for utilities. These chases and architectural decisions are required really early on in the process to allow for MEP integration into these types of buildings. This office building in Portland, where a beam-free colonnade runs up through the middle and is created by spanning CLT over that beam gap, provides an area for the mechanical passages like we saw in the previous slide. So here we're taking that idea and then applying it at scale across a multi-story building. Well, projects like these often start from a big idea and lead to just a sketch to kind of rough out that idea. But very quickly that leads to the model, and eventually the model leads to machine and fabrication information, and then site work is really just assembly of the components. The true building and decision making happens back at that modeling and reviewing stage of the project. In this example, thinking through this big idea early on in the process allowed this particular design to be streamlined into just a few repeatable components shown on the right-hand side, showing the snapshot of all the machine files. This is really only possible when the virtual building process can happen very early on. And here it is being installed. Planning for site tolerance is also a critical part of the design process. We do have different site existing materials coming together with off-site fabricated materials, and having appropriate gaps and planned spaces will facilitate the site installation. You can see in the picture on the right that there are some gaps and spaces, and that needs to be planned in to make everything fit as planned. So a little bit away from mass timber, but parallel processing helps schedule time-constrained jobs. And this is an example with bathrooms. The smallest room in the house are typically occupied by many different trades on site. Plumbers, electricians, tilers, finish carpenters, they all need to work in this smallest room of the house. And having this as a finished product improves and relieves coordination on site. The room kind of becomes the fixture that gets installed as a finished product. This is common in the hotel industry, and as we saw in the earlier slide on cruise ship construction. But with the model and the early involvement of all the trades, there's no reason this can't apply to residential construction as well. The details, when they're finished in the factory, lead to higher quality, high value space, which is worth the shipping cost. There's a cost for shipping units that are larger and take up a lot of space, but as long as the space is high value, then it's worth the shipping cost generally. Another example of high value space here with consolidated mechanical cores. Pre-building mechanical cores results in rapid construction for mechanicals on site. This example with an attic ridge wall optimizes plumbing work done first in the model, then in the shop, not in the attic on the site. And all of this results in reduced site time, benefits of parallel processing, and it again is only possible if it lives in the model initially. Here's another example as we were talking about integrating site existing conditions versus what you're building in the shop. This has fully modeled concrete and how it integrates with timber. With everything modeled, all fabrication can happen off-site, which results in high productivity, reduced site impact, and typically this also means a lot less waste is generated as well. Definitely less waste generated on the job site. Seeing some of the production of these parts early on in the process, probably while concrete is actually being poured, with beams cut to length, finished, and hardware even attached in the shop. And then what arrives on site, again, is really a kit of parts for assembly. It's not about fabrication on site, it's about assembly. These columns are all prepared for the thickness of the CLT. They have hardware installed on them. and they're ready to start assembling on site. So this job was the first time a crew worked on a mass timber job, and they were very successful and efficient with the process. All of the work done by the teams during the coordination and virtual building phases make the site assembly process more straightforward and more predictable. So another study here showing some parts manufactured in various locations and all fabricated off-site, but here it is coming together on-site. The glue lambs for this particular job were from Canada. You can just see the basic structure of this building, kind of an armadillo-shaped building here. The panels were from Walpole, New Hampshire. The curtain walls were actually from Germany. The copper roof, which you'll see eventually in some of these pictures, was built in New York, and no test fitting was needed or was done on this job. And when the components come together on site, they fit since they're modeled together. Everyone relies on the model to know that this will happen successfully. Here you see the building taking shape and actually shedding water by the end of the roof being installed. And then here you see the roof all prefabricated in New York, the copper panels. We actually sent them the surfaces from our CAD model, and they built directly from those electronic files and then just installed on site. And they were building those roof panels well in advance of that building existing on site. So again, gaining the benefit of parallel processing by being able to reference that model and having all the teams involved early. So this curtain wall from Unilux that they built in Germany was also directly exported from our 3D model. And early on in the process, coordination of the structure was considered and decisions were made about which team would take the loads. And Bensonwood took the loads in the timbers, which led to thinner framing in the glass panels, which allowed the glass to have a much more airy look to it. Even the board layout on this job was modeled very specifically. You can see that the speakers are the size of 3 boards, and lights were justified to the board layout in the ceiling. Again, the question, does it have to be in the model? And the answer is definitely yes. If you, the board panel layout was a particularly complex process, and that was all modeled, and we provided layout for all those boards. You can tell with the different radius in the timbers, those boards are actually a fanned pattern, and laying that out on site would be extremely difficult, especially because the spring point for the layout would be down in the ground about 50 feet. So we laid these out in the model, exported that information, and provided structural ribs on the back side, which actually gave the layout for all the different board positions. So all the speakers modeled, all the lights modeled, and the board layout actually converted into a physical layout pattern that we installed on site. So these are quite a few of the different decisions that need to be considered for jobs like this. And to address all of these, again, we're going back to how important it is to have early collaboration of all teams to make it possible for successful completion of jobs like this that are quite complicated. There are a few reasons why you might choose on-site versus off-site, and here are a few reasons listed. One of them that can push you to on-site construction justifiably is if clients want to make field adjustments and decisions as the project goes along. So that would definitely lead you to needing to follow on-site construction practices. Difficult sites often lead to the need to construct off-site. And there are the points about off-site requiring early decision-making, as I've been talking about, and there can be possible higher construction costs in some of those areas, but the resulting speed that you get on-site often can offset those higher costs. Here are a few of the considerations of entering the realm of off-site construction, especially with mass timber. with this early building process, you definitely need space, both with an offsite shop that can handle these materials and also on site to handle larger components than typical. As we've been discussing, you need to build this construction team very early in the process and agree upon how you'll store information with all the different partners engaged in the process. And again, there's the need to rely on the model and include everything possible in that model so that it can be referenced throughout the project. So a couple concluding thoughts here. You can look at these mass timber projects in a couple different ways. And one is as a real challenging prototype that has some isolation between design and execution, where the process is difficult and it's hard to correct poor choices that were made early on. You can definitely pick a job like this apart and look at it as being quite a challenge. But you can also view it as an opportunity to collaborate and embrace this early virtual building team and this decision-making process to create a model that will provide answers and solutions coming from this collection of expertise in the real early part of a project. So with that kind of a mindset, these can be very successful. One final comment here is that the building code, and Chris touched on this as well, but building codes and inspections are different depending on the location, and the code official is another key player to have as part of that team right from the start. So it's something to also think about as an important member of the initial team. So thank you, and I look forward to some Q&A after Justin talks about the assembly process and logistics of what happens on site with these projects.